So now we've seen that in the presence of a crystal field, in an octahedral environment, the d orbitals change their energies. These orbitals that are written here, that is these three orbitals, together they are called T2G orbitals. T for triplet, and this is the symbolism that comes from group theory. T2G orbitals. These orbitals over here are called EG orbitals. Okay, so EG orbitals are the these two orbitals, and the T2G orbitals are these orbitals. The easy way to remember is that T stands for triplet. Now let's change the environment a little bit. Instead of an octahedral environment that we've studied, let's look at a tetrahedral environment. The same ion, 3D, one ion, one electron in the d orbital placed inside a tetrahedral environment. And we assume that the symmetry is once again cubic. Now for this particular environment, the orbitals will remain the same. One needs to write down the appropriate potential function. Now the appropriate potential function is, this means that one needs to write down the coordinates of the anions. So if I draw a cube over here, each side of the cube has dimensions A. So suppose this is the position of the anions. And the origin is the center of this cube. If the origin is taken to be the center of the cube, then, and this is the x-axis, this is the y-axis, this is the z-axis. The coordinates of this point are a by 2, minus a by 2, and minus a by 2. The coordinates of this point over here, they are minus a by 2, a by 2, minus a by 2. The coordinates of this point over here are minus a by 2, minus a by 2, a by 2. The coordinates of this point are a by 2, a by 2, a by 2. Now I insert these coordinates into terms of this kind. So I have 4 variables. I just put these, each one of these into terms of this kind. I can generate the potential. Okay. For example, if I take this coordinate, this will generate a term of this kind: x raised to power x minus a by 2 whole square plus y plus a by 2 whole square plus z plus a by 2 whole square under root. So I will generate 4 terms plus 3 other terms. And I multiply this with q over 4 pi epsilon naught. I will get the potential. Okay. Now I want to express everything in terms of the distance of the central metal cation with the ligand D. Okay, I would like to express everything in terms of D, because when I looked at the octahedral environment, I expressed everything in terms of D. Now the relationship between A and D is following: A over 2 is D over under root 3. Okay, so you can look at the geometry and work this out. So each A over 2 can be replaced by a D over under root 3. Hence, I am able to generate the potential for a tetrahedral environment. Okay, now let's move to Mathematica and solve this problem for a tetrahedral environment. And the results will be quite interesting. So now I have the luxury of using a template that I've already built. I just put x back to normal, y back to normal, z back to normal, and I define t equals d by square root 3. I define this. And then I write this x. Okay, so this thing, all of this is going to change. I have phi b is x minus t. A over 2 is d over under root 3, so x minus t square plus y plus t square plus z plus t. This is just one term. I need 3 more terms. X plus t, x plus t plus y minus t plus z minus t plus x minus t plus y minus t, z minus t. Plus another term, x plus t plus y plus t minus z minus t, z minus t. So here I have z plus t, y minus t. Let me counter check this, because once I get this wrong, there's no coming back. X plus t plus y minus t plus z plus t, x minus t plus y minus t plus z minus t plus x plus t plus y plus t plus z minus t. Okay, so now this is the potential. In units of q over 4 pi epsilon naught, I convert this into a series. Might take some time over here because it's slightly more challenging for Mathematica to convert this into a series. So I'm truncating this expression to a certain number of terms, and I'm justified in doing so because I have terms of the kind of 1 over d5, a over d5. A is much smaller than d, of course, so higher powers will be much smaller. So this might take some more seconds. So I think the major idea in quantum mechanics that we've been employing so much is the perturbation theory, especially the degenerate perturbation theory. And you see, in orbitals of this kind, the concept of S and J quantum numbers has broken down. It's just broken down. Concept of S and L is just broken down. What will be the orbital angular momentum of these states? We don't know at the outset. What's going to be the J of this state? We don't know out yet. We have to fill in electrons into these orbitals nevertheless. Right now we're talking about just one electron going into this energy manifold. Of course it's going to go into the lower state. In this octahedral environment, it's going to go into one of the T2G orbitals. And this delta is the crystal field energy.
So for these to express them in the Dirac notation?
These days?
Yes, sir. What would we use? What are the symbols that we would?
Here I would use, initially I would use L and L. L and M. We're talking about single electron. Okay. So now this has worked out. I define my H again. S2 is this thing over here. If I would like to look at S2, look at the face of S2, this is the expression that I get. Let me delete the older ones. This is my S2. Now once again you observe that there are x raised to power 4 terms, x y4, z4 and x square y square, and there's an additional xyz term over here. Okay, so this is the tetrahedral potential. This term at the beginning I don't care about. Okay, I don't care about this because it just gives a reference potential, it just gives a bias which does not contribute to the energy, and I call all of this thing here V. So now I've defined my V. Now if I look at this term over here and I put this on the blackboard, I can see some interesting behavior. My V now, the function of x, y, z is minus 14 over 9 d5 let's call this plus 14 over 95 minus x4 minus y4 minus z4 plus 3 x square y square plus 3 x square z square plus y square z square and an xyz term, okay, and an xyz term plus some coefficient, let f into xyz. Now when I integrate this term over all of space, no matter what orbital I take, I get 0. Let me check this. Okay, because this is x, y, z. When I integrate this over all of space, positive x, negative y, negative y, I get 0. So this term doesn't actually matter in the calculation of the energies. But what you observe here is in the tetrahedral environment, these product terms and these terms had opposite signs, but now the direction is reversed. These terms come with a negative sign and these terms come with a positive sign. Now this has a bearing on the energies. Okay, let's see how. So my orbit, the radial part of the wave function remains the same. All the other orbitals remain the same. Nothing happens to the orbitals because I'm calculating perturbations in the energies of these orbitals, d1, d2. All of them are the same. Conjugates are the same. Now I can define x again, y again. This is my v, my new v. First of all, what I would like to do, I would like to see what happens when I put x, y, z here. I get 0. So the x, y, z term does not contribute anything. It's an odd function. So when it's integrated over all of space, the answer is 0. So from the v, I can be kind to Mathematica and I can remove this term. I can redefine my v, and by removing this x, y, z term, okay, it doesn't matter. So this is my new v. Okay, you know that term is odd, is an odd function. So this is my new v. Now I calculate the energies. E1, and I put v here, put v back here. Okay. I get some energy. Now this turns out to be negative. Previously these were positive energies for D1 and D2. Okay. E3 turns out to be now positive. Previously it was negative with respect to the unperturbed energy levels. So now it seems that the EG states have come down and the T2G states have gone up. Right? So now the effect of the tetrahedral environment can be summarized in the following fashion. This is the unperturbed energy level before the crystal field perturbation. All 5d orbitals are degenerate in an octahedral environment, OH. The triplet states, T2G, are lower in energy and the EG states are higher in energy. And this is up 3 units, this is down 2 units. EG. This is the octahedral environment. This splitting is delta octahedral. Now for and we know that T2G are, we know what orbitals these are and we know what orbitals these are. For the tetrahedral environment, TD, what we observe is that the ordering reverses. The T2G orbitals, which are D3, D4 and D5 now have higher energy. These are the T2G orbitals. And the EG orbitals have lower energy. And this splitting is the crystal field splitting in a tetrahedral environment for a D1 orbital, for a D1 electron. This is not the same as this. And this, it's obvious from the number that this is smaller than this. Okay, let's find out how small. Delta tetrahedral is from the expressions over there, barring a q over 4 pi epsilon naught factor, E q over 4 pi epsilon naught, A naught 4 over D5. This is 7560 plus 11340. E octahedral is given here. So if I would like to find the ratio, it's 7560 plus 11340 divided by 25 515 plus 17010. Let's see what this is. Four over 9. For D1 orbital, the tetrahedral splitting, crystal field splitting, is about 50%, slightly more than 50% of the octahedral splitting. And the ordering has now reversed. Now these three orbitals, which are dxy, dxz and dyz, have higher energies, because in a tetrahedral environment these orbitals land electronic densities closer to the anions. And if you have a dz square orbital, for example, if you have an orbital of this kind, then the electronic density is avoiding the electrons. So this has a lower energy configuration. And you have the dx square minus y square has lobes of the density which are also avoided, which are along the x and y axis, whereas these are along the diagonals. So the overlap of the electrons with the point charges is minimized. Hence the ordering has now shifted. So depending upon the environment, crystal field splitting can give you different kinds of energies, different kinds of energy manifolds. Alright. Now what we would like, so you can have different kinds of environments. You can have a planar environment in which this is the central metal atom and these are the electrons, the anions, sorry. So I can ask you in a homework to find out what kind of degeneracy lifting takes place for this kind of system. For this dihedral system, this belongs to the symmetry group D to H. So depending upon the environment, these levels can be split up in different ways. Suppose I have an octahedron in a cubic environment. Now this is a perfect octahedron. If I stretch this octahedron, and the way I stretch it is that I elongate along this axis and compress along this axis. So all of this squeezes. This octahedron will now be distorted. It's going to be a distorted octahedron and it will no longer have cubic symmetry. If I equally compress it along this plane and extend it along this axis, then it's going to be what is called tetrahedral symmetry, in which there are two kinds of distances of the metal atoms with anions. This one is the distance along the axis and one is in the plane. If I stretch it even more cruelly by having this stretching to be different from this stretching, I can have three kinds of distances between the metal and the anion. Then it becomes an orthorhombic environment. So now if I have a perfect cubic environment octahedron, and if I stretch this octahedron, D then C can be lifted even further. Okay. Now I want to show you this, how this happens, because it has an important consequence, which is called the Jahn-Teller Effect. Now let's take this perfect octahedron and stretch it along one dimension. So I have two kinds of distances now. Now I'm not going to repeat this over and over again, so I'm going to use something that I've already written, that I've already calculated. Alright, so let's move back to mathematics and let's look at this for the time being. So now I have this phi b. I have two kinds of distances. One is d and the other is, I call it m. Two kinds of distances. It's a tetragonal environment. Tetragonal symmetry, an octahedral environment, tetragonal symmetry. I simplify this. This is my sum, and then I look at S2, I do some simplifications. This is my new potential. Okay? Now it's slightly more complicated, so I'm going to use this as a starting point for the potential. I put this potential in here. My V is this. This is my V. Now I define X again, R, Y again, Z again. Now I would like to put this V into these energy calculations, the energy corrections. I've defined a V. I can actually leave out this first term. Okay. Now I have different kinds of terms. You will notice. I have terms in which there is a 1 over d cube minus 1 over m cube. I have to preserve this. D is not the same as m. If d is the same as m, I will recover the cubic symmetry case. Now I calculate the energies. The energy for d1. Might take longer because it's a slightly more complicated integral. Here are the results. Okay, it's gone. Okay. This is one energy. Let's look at another energy. Each one of them is going to take some time. So it's better if I shift it to the results. The results are similar to what I have here. I have 5 energies, E1, E2, E3, E4 and E5. Let me run all of those energies in the background. So I have 5 energies. Energy for one orbital, energy for the other orbital, third orbital, fourth orbital and the fifth orbital. You will notice that this is different from this and it's different from this. 2 orbitals D4 and D5 have, however, the same energies. Okay? So now you get additional splitting. This energy is, these 2 energies are the same. This is for D4 and this is for D5. So what happens is that because of the distortion of this tetrahedron, originally our octahedron was like this. These were EG, these were T2G, this was EG. Now what's going to happen is that two of these levels will change their energy. Okay? And how will they change their energy? We have to figure out whether they go positive or negative. And this could be done if you do the proper calculation and put in the different kinds of values, whether the stretching is like this or whether it's like this. It will change the result. But in any case, two of these levels go down, one of these levels goes up, or vice versa, depending upon how is the octahedron stretched. One of these levels goes down and the other level goes up. So this is further split. The degeneracy in the T2G level is further split, and this degeneracy is further split. This is the dxy, dxz and the dyz orbital. This is the dxy orbital, and this could be, say, the one of them could be the dz square, the other could be the dx square minus y square. So by stretching this octahedron and breaking the symmetry, reducing the symmetry from cubic to tetrahedral is going to lift the degeneracy even further. Likewise, if you have the tetrahedral environment, you stretch or distort the tetrahedron, this degeneracy can also be lifted. Now this is our first linkage of magnetism with elasticity, with the dimensions of the material. Alright? So keep this in mind, and in the last 10 or 15 minutes I am going to present some interesting applications of all of this.
Sir,
Yes?
just a small question. So when we have the machinery to understand the behavior of energy levels with respect to these various perturbations, this or the others that we have done before, so then we apply to the machinery that we developed in this first few lectures about paramagnetism, where we derive the partition function and then we see the behavior of magnetism.
So you need the value of J. But here there is no concept of J so far. When you put that ion into a crystal, the concept of J has actually broken up, because it is the crystal field that is dominating the stage, and these new energy levels are built up. Now suppose we have a situation like this, a perfect octahedron, cubic symmetry. Let's call this the crystal field splitting. Suppose you have an ion, a 3D ion D3 with 3 electrons in it. Okay? Now where would these electrons go? Once this crystal field has split these levels, it has determined the stage, it has determined the placeholders for where the electrons can go. Now you can apply Hund's rules. Okay? Because the Hund's rules are a manifestation of the exchange interaction, the spin orbit interaction. Okay? Those determine the Hund's rule. Now the stage has been set by the dominant crystal field interaction. Now you have to put 3 electrons into these placeholders. The first electron of course will go to the low energy state. This has place for 3 electrons. So you would like to maximize S. So you put 1 electron here, 1 electron here, 1 electron here. This is the crystal field. This is a gap. This is an energy barrier. Suppose you have the ion T4. Okay? An example of a D3 ion, if you look at the periodic table, could you give me an example of the 3D ion, D3 ion. If you have the periodic, do you have the periodic table with you? Can you give me an example of D3? Three electrons, chromium 2 plus, vanadium 2 plus. For example, vanadium 2 plus. The period is scandium, titanium, vanadium, chromium, manganese, iron, nickel, cobalt, copper, manganese. Okay, and there are two, potassium and calcium here. So D3 is V2 plus. It has lost 2 electrons and it still has 3 electrons. So this is vanadium. D4 could be chromium 3 plus. 2, 3, 4. Chromium 2 plus. This could be chromium 3 plus as well. D3 is chromium 3 plus as well. So vanadium 2 plus, chromium 3 plus, both of them are D3, chromium 2 plus is D4. So you have 3 electrons and they go in here. Suppose you have a 4th electron. For example, you have this ion, chromium 2 plus ion. Okay? Now what you would like to do, or you have the important ion manganese 3 plus. So there are 4 electrons. In this case, where will the 4th electron go? Will it go here? Or will it go into one of these levels and invert its spin? Now Ohm's rule, if you were to follow Ohm's rule, that 4th electron must go here. But then that would mean that the Ohm's rule is ignoring this crystal field energy. So now you have to look at, if you want to place your 4th electron, you would have to look at what is the relative size of the crystal field energy and the Coulombic energy. This Coulombic energy determines the exchange interaction as well. If this is large as compared to the Coulombic energy, then the 4th electron would actually like to remain within the T2G manifold. Its Coulombic energy is going to go up because you have an electron in the same orbital and there is electrostatic repulsion between the electrons, but the increase in energy is much smaller than the increase in energy which would have accrued if that 4th electron would have gone here, because this term is much larger than this term. So if you want to put a 4th electron, there are 2 choices, either put it here or put it here and invert its spin. So if you put it here, this term goes up. If you put it here, this term goes up. But this term is much smaller than this term. So the energetically favorable situation is that if this condition is satisfied, then the 4th electron goes here and inverts its spin because it has to satisfy the symmetrization postulate. So in this is the case which is called the strong field case, which tells us that the crystal field is strong. It's stronger than the electrostatic term. So the 4th electron will actually go here. If this field is strong, the 4th electron in manganese 3 plus or chromium 2 plus is going in here. Then if you calculate the spin of this material, of this ion, it's going to be 1. These 2 spins cancel out and you have half plus half is 1. Okay? So now this is effectively like a triplet. This is S equals 1. If on the other hand you had a scenario in which you have the converse situation. U is much larger than delta. That is, the Coulombic effects dominate. The exchange interaction dominates. Then Hund's rule will be satisfied, because the Hund's rule are just a manifestation of the exchange interactions and the Coulombic interaction. Then you have 3 electrons. No doubt they will go into these levels with their spins in the same direction. The 4th electron will go here, and it will maximize S, just like Hund's first rule. So this is the situation which is generally called the weak field case, and the word crystal is omitted. Strong field means strong crystal field, weak field means weak crystal field. In this configuration, S equals 2. This is called the high spin case. Weak field gives you high spin. This is called the low spin case. In this case, Hund's first rule is satisfied. Here, Hund's first rule breaks down. So strong field leads to low spin. Weak field leads to large spin, because the spins can go into the higher orbitals. Because delta is smaller than U. The cost of increase in energy by going to a higher crystal field split level is much smaller. It's smaller than the cost of energy of putting this electron into here, because that will increase the repulsive energy between the electrons. So depending upon the relative sizes of the Coulombic, that is exchange, and the crystal field interaction, you can have low spin configurations and high spin configurations. And this configuration, the low spin can go into high spin configuration if you excite this electron. It can be happen through temperature. A phase transition can take place between the low spin and the high field versions. Okay, a phase transition. Now, interestingly, if you look at the strong field case, and this is the weak field case. You look at the weak field case. Now there is this 4th electron, a single electron in a degenerate level. Let me redraw this diagram. I'm going to talk about an interesting phenomenon in the last 5 minutes. I'm talking about manganese 3 plus ion, which is 3D4. And I'm talking about the weak field case, which is high spin. All of this works together. So I have the T2G orbitals and I have the EG orbitals. 3 electrons, of course, go in here. That single electron is in a degenerate level. Now look at this distorted octahedron over here. Okay? If I distort this octahedron, what's going to happen is that 2 levels are going to go down. One level is going to go up. Now there are 3 electrons inside this manifold. So 2 electrons, if these electronic populations carry over to this distorted octahedron, 2 electrons go here, 1 electron is here. Now what's the energy of this manifold as compared to this manifold? Is it lower, same, or higher? Same, because even though there are 2 electrons with lower energy, but this is 1/2, this energy perturbation is 1/2 of this. So this, nothing happens. There is no advantage in distorting the octahedron for these 3 electrons. However, look here. One energy goes down, the other energy goes up. This thing here. And there's only one electron here. So that electron carries over to the low energy state. Now is there hence, if this is the configuration of manganese 3 plus ion, is there an energetic advantage for the octahedron to distort? Yes, because there is only one electron in a degenerate energy level. There is no electron over here to compensate for the decrease in energy. So overall the energy of this ion is lowered. Therefore, if you have manganese 3 ion, it prefers the distortion of the octahedron because that's going to lower the energy of the system. Therefore, the octahedron is distorted. There is a strain that develops in the crystal. This effect is called the Jahn-Teller effect. The automatic distortion of, the preferred distortion of an ion whenever there is a lone electron in a degenerate pair. Now this lowers the energy of the system. Suppose it lowers the energy of the system by A is a constant, by A minus A into some, this is the strain, right, elastic strain. However, when there is a strain in the system, the elastic energy of the system goes up, it's in a strained condition. So there is also an increase in energy, BE square. This is the elastic increase in energy, this is the electrostatic advantage afforded by the decrease in energy, by the distortion of. So you would like to make all of this negative for an ion to exhibit the Jahn-Teller effect. This has to be negative because you want the overall energy to go down. So manganese 3 ion is an important ion which exhibits this effect. Another ion is copper 2 plus. Copper 2 plus, if you notice, is on position number cobalt, copper. Copper के बाद क्या आता है? यहाँ पे आखिर में zinc. It says 9th position. So copper is 3d9. Okay. So 3d9 means there's one hole here. 10 electrons will fill up these levels. The scarcity of one electron means there's one hole here. So one hole is the same, a hole is the same thing as an electron. This ion will also exhibit the Jahn-Teller effect. There is one lone hole in a degenerate level. Electrons and holes can be treated totally equivalently. It's only that these energy splittings are reversed because hole has a positive charge. Okay, so this is the Jahn-Teller effect. In the next lecture, next week hopefully, I'm going to talk about some more applications of this. I'm going to talk about one of the most important ions, iron ions. Remember, still we are not dealing with delocalized electrons. The electrons are bound to some atom or ion. We have not yet given electrons the freedom to roam about in the metal, which means we are only discussing localized magnetism so far. When the electrons can roam about in the metal, we have itinerant magnetism or band magnetism. So far we have only focused on electrons that are hooked or latched onto fixed positions inside the solid. Okay? Most probably I will not be here on Monday. So on Monday what I'm going to arrange is Ali Akbar is going to give you an overview of on Blackboard of vibrating sample magnetometry. How do you measure magnetic moments? And then there will be a demonstration in the VSM laboratory. Okay? So you will assemble in the conventional classroom at 1 p.m. After half an hour overview, a diagrammatic representation of VSM is going to take you to the laboratory and it will actually show you how to take a magnetization curve. Okay? Thank you very much.